Okay, I'm going to walk through how to solve some of the problems from the workshop on likelihood functions. And so I'll assume you've read all the notes, and I'm just going to start with problem number 1 here. It says some geologists set up monitoring equipment to find out how often a small island has major earthquakes. Let x be the time until they detect the first major earthquake, and assume that x is distributed with an exponential distribution with lambda as the parameter. So then we know what the PDF is. We can look that up. That's this function, lambda times e to the negative lambda x. And that's basically also the likelihood function. The PDF and the likelihood function are going to be the same. You just think about them in different ways. The PDF is a function of x, and it tells you the probability density. The likelihood is a function of lambda, and when you put lambda in as the input, you think of x as a fixed constant. And so that's it. We just copy the function as our solution. So the likelihood function is lambda e to the negative lambda x, except we know that x is 4 in part A because that's when the first earthquake supposedly happened. Okay, so that's it. Likelihood functions are just another way of looking at PDFs. Now, one thing to know about it, it's not a probability function. So the temptation is to say, oh, that's the probability density function for lambda, and that's not true at all. It's something very different. Really, what you can get out of a likelihood function is you can get like a comparison of, say, two different possible values of lambda. You can say one is more or less likely than the other. But the likelihood doesn't really have a meaning unless you're comparing different possible values of lambda. Okay, question 2 then asks, how many times more likely is it that lambda is 1/5 than that lambda would be equal to 1, according to this likelihood function? And so what you do is you plug in 1/5 into the likelihood function, and you get this. I just used a calculator. And then you plug in 1, and you get that, and then you can clearly see that 0.09 is bigger than 0.018. And in fact, it's about, if you divide them, 4.9 times bigger. So it's 4.9 times more likely that lambda is the small number than that it's equal to 1. And then in part C, I ask to take the derivative of the likelihood function to find the value of lambda with the maximum likelihood. So I took the derivative, and to take a derivative of a function like this, you need to use the product rule, right? And so I'm going to skip all the steps and just give you the answer here. And then when is this derivative equal to 0? Well, it looks to me, the exponential part's never 0, so I guess it's when lambda equals 1/4. And then if you double check a graph of the function, which actually, let's see if this works. I'm going to try to graph the function here. I'm going to pull up Desmos really quick. And let's see, Desmos, and start graphing. And the function I'm trying to graph is that likelihood function, which was the function, where was it? Not the derivative, the original likelihood function, lambda e to the negative 4 lambda. And so I can't use lambda, I got to use x times e to the negative 4x. And there you go. Let's zoom in on that likelihood function, and we can see, sure enough, it does have a maximum, and that maximum is right there when the input is 1/4, just like we said it was. All right, perfect. So that's the solution there. The maximum occurs when lambda is 1/4. And if you think about what lambda represents for an exponential distribution, lambda is the rate at which whatever the exponential thing is measuring happens. So this is saying you get one earthquake every 4 years is the most likely value of the parameter lambda. Okay, so that makes sense. Okay. All right, number 2 was a second question that I asked you to try. It says you visit a large university and are wondering how many students are science majors. You pick one random student and find out that she is a science major. Let x be the random variable representing whether a student is a science major, and we're just going to say it's 1 if they are, 0 if they're not, and assume that the true proportion of students on campus who are science majors is p. So that's our parameter. And so we're trying to find the probability distribution for this parameter for x, and its probability mass function. Well, so we're randomly picking one student, and they either are or are not. So these are binary outcomes. So that's a binomial distribution with one individual, one sample size. And so then the binomial distribution, you can look up what the density function, or probably mass function since it's discrete, for the binomial distribution, and there it is. And p is a parameter, x is the actual value that we might get. We might either get 1 or 0 science students in our sample. Okay, cool. Now change that into a likelihood function. You just change perspective. You take this formula and you plug in the value of x that you know. And we know that right now x is 1 because the one person we asked was a science student. So I plug in 1, so it's p to the first, and then 1 minus p to the 1 minus 1, which is 0, and anything to the 0th power is just 1, so it goes away. So there's our likelihood function. It's really simple. The likelihood function for p, given that x was 1, is p. Okay, that's it. And then finally, for problem 3, if instead of interviewing 1 student, you take a sample of 6 students, and 2 out of the 6 students were science majors, then you can think of the number of science majors as being a sample from a binomial distribution with 6 as your n. And then the parameter p is still there. We still don't know what it is, but we can make a likelihood function for that parameter p. But now we've got to go and find the probability density function for a binomial distribution. And for all of these probability density functions, it's a good idea to, I'll go ahead and pull up the website here and take a look at this. So you want to go and look at all of the software and handouts sheet that I had, posted a long time ago. You can use this probability distribution sheet here to look up the probability mass function for a binomial distribution. So when n is 6, you have 6 choose 2, and 6 choose 2. What is 6 choose 2? What is it? 6 times 5 divided by 2 times 1. So 30 divided by 2, 15. So that's where that number 15 came from. And then the rest of this, it's p to the k, and we happen to know that the k is 2 because there were 2 science majors in our group of 6 people. And then the rest, the other 4, were non-science majors. So there we go. That's the probability mass function, but with the outcomes plugged in and the parameter left unknown. So then it becomes a likelihood function. Okay, cool. So there's our likelihood function. Notice I'm writing it without expressing the reminder that it's given that our actual outcome was 2. People do that sometimes just to emphasize that the likelihood function is a function of p. All right, finally, I'm supposed to show that the maximum value of the likelihood function of p, given that x is 2, occurs when p is 1/3. And this is a really big hint here, and we're going to use this a lot. When you have a likelihood function, it's really helpful oftentimes to not work with the likelihood function itself, but to take the logarithm of the likelihood function. And the reason that's so helpful is logarithms will split up a function like this that's a product of a bunch of different factors into a sum. And then when you do calculus, it's way easier to do calculus with a sum of terms than with a product of factors. And so that's what I did here. I took the log of the likelihood function above, so that just becomes the log of these pieces all added together. And then remember, you can pull powers down, so the 2 gets pulled down in front and the 4 gets pulled down in front. And so you have this really easy thing to take the derivative of. And if you maximize the log likelihood, that's going to happen at the same p-value where the maximum of the original likelihood function, where this has its maximum, right? Taking the logarithm doesn't change where the maximum it is, it just would change how high up, but we don't really care about that. Okay, so this is what I'm going to take the derivative of. It's really easy to take the derivative of this because the derivative of the constant term goes away. The derivative of this is 2 over p, and the derivative of that is 4 over the derivative of the inside. 4 over the inside times the derivative of the inside, which makes it negative. That's where the minus sign's coming from. And so then you just have to solve for when this is equal to 0. So write an equation, cross multiply, and do a little algebra, and you should figure out that in fact p is 1/3 is exactly the location of the extreme point, and then you can use a first or second derivative test on this formula to check that that really is the maximum. You could also graph this on a graphing calculator and check that the p, where this is the highest, is 1/3. Okay, that's it. We're going to take a look at other more complicated examples, but this 3 was sort of a preview of what's coming next. Is what happens when you take a sample of more than one observation. Now in 3 we could sort of just pretend it was a single observation from this binomial distribution where we had 2 successes, but in other situations we're going to have to do sort of a joint distribution function, and then how do you do maximum likelihood with that? Well, we'll talk about that on Wednesday. All right, as always, if you have any questions, please let me know. I hope you found this video helpful.